Hello. In this video, I will give a brief demo of our work on text-to-triple translation in the form of a Python Flask web application. So you may already know from the papers that the system is based on the sequence-to-sequence model. So in this demo, I will show you how we use it to generate triples. To be precise, RDF triples. So here we just simply start the application first. So in this video, we loaded the model we trained from the Wikipedia DBpedia dataset. And the reason why I use this dataset for demo is because I also want to show you the effectiveness of the knowledge graph embedding, which we trained from over 2 million DBpedia triples using the transient model. So after we refresh, it started. So you see the current loaded embeddings is Wikipedia dump for the word embedding and the DBpedia dump for the knowledge graph embedding. We have a default sentence here saying New York City is a city in United States. So as an output, the decoder will generate 3 outputs with a sequence of SPO. And here, since this dataset is aligned with DBpedia terms, so it's easy for us to verify the content of each output. So this is also another major advantage of the system because our end-to-end application provides you with a complete ready-to-use RDF triple. There's no intermediate step or further ontology matching. So no pipeline-based or pre-process or linking or predicting is needed. So let's try another example. For example, if we say Berlin, which is the capital city of Germany, like if we say it's the city Germany. So we have Berlin, country, Germany. And if we say Berlin is the capital city, okay, so the result is expected to be hypernym, which is similar to class and type city. This is because the attention is focused on the city rather than the capital. So at the current stage, we only consider the situation where a sentence generates one single triple. That means the generation of multiple triples and the identification of overlapping relations are not in the scope of this work, but they are definitely in our to-do list. So if we remove the city, just saying Berlin is the capital, I think the result is expected to be different because the attention mechanism applies. Yeah, so now the attention is focused on capital. So if we say one more capital related example sentence, we say Spain's capital city is Madrid. So by saying this, the attention, the predicated attention, might focus on the middle part of the sentence, which refer to the relation, because the two ends are subject and object. So here we see actually capital is now used as a predicate to describe the relation between Spain and Madrid. And it's important to mention that this capital is different from the capitalized capital we just saw, which is actually an entity. This is a property, which refers to the relation between the two entities here. So let's try a person's example. If we say Bruce Lee is from United States, we get Bruce Lee country, United States. And if we say something very popular on Wikipedia, saying Bruce Lee was born in San Francisco, so we are expected to translate it into a very popular predicate used on DBpedia, which is the birthplace for persons. I think there's over 1 million triples. If you want to dump all the person triple in an endpoint, you will see birthplace or birth date a lot. So if we say something related to occupation, saying Bruce Lee is actor, we have Bruce Lee occupation, actor. So another interesting thing here is I want to show the effectiveness of the knowledge graph embedding. So suppose we have this sentence saying Chaplin is artist. So the user might referring to Charlie Chaplin, which is the common sense. But actually in our training data, we don't have Charlie Chaplin as the natural language text as the training samples. But we do have Charlie Chaplin in DBpedia triples, which we use to train the knowledge graph embedding. So the model will try to decide which Chaplin this is and pick a Chaplin instance from the DBpedia persons. So how it generates Charlie Chaplin, but not other Chaplins, it's largely because of the vector space distance by using this occupation as age. It's closest to the artist object node. So this is one example of why the knowledge graph embedding is working, and also will improve the performance. And another example can be if we just simply change the person's name from switch from Chaplin to Bruce Lee. Let's see what will happen. So this time, we are saying the same occupation, saying Bruce Lee is artist, which is the same to the previous sentence. But the object is different. Now we are outputting martial artist rather than artist. That is because in the KG embedding, Bruce Lee is actually, by having this occupation, age, he's linked to actor, martial artist, philosopher, filmmaker. So this is why even we type in artist rather than martial artist, we are still getting the correct triple, which is aligned with the DBpedia knowledge graph. This is another good example of showing the effectiveness of the knowledge graph embeddings. So I hope these simple examples will give you a basic sense of our system. And we welcome you to train and deploy your own version, and also provide us valuable feedbacks in the future. Thank you very much.